Assalamu alaikum everyone. This is Circuit Analysis 2 and the course code is EE-212. Today we will be discussing about the energy analysis of the RLC circuit. But before that I will be just summarizing the last lecture. In the last lecture we discussed about the transfer characteristic of the series resonance circuit. We started from the voltage gain formula of the RLC circuit, where V in was the input voltage and we were getting the output voltage across the resistor, and the V out over V input, we got the formula for that by applying the voltage dividing rule, the voltage divider, and this V naught over Vi, this is known as gain, and this is the transfer function of voltage gain. Then we found out the gain magnitude as well as phase, and after drawing the graph for the gain magnitude, we just got information that it is a band pass filter. So there were two frequencies that we find out in the last lecture. There was a lower cutoff frequency and there was a higher cutoff frequencies, and these two corner frequencies or cutoff frequencies defines the bandwidth of the band pass filter. And by bandwidth we mean that the signal will only give you an output if its frequency is within the range of omega low and omega high, and this omega naught is the resonant frequency. Then later we calculated the formulas for the lower and upper cutoff frequencies. The first formula was in terms of only the circuit elements, resistor, inductor and capacitance, and the second formula we found out in terms of the resonant frequency and the quality factor. After that we formulated a relationship between the bandwidth and the quality factor, and we found out that the bandwidth is inversely proportional to the quality factor. So if the quality factor is increasing, the bandwidth will decrease. So with the increase in quality factor, the band pass filter will become more selective. So if the quality factor is decreasing, bandwidth will increase. So after that we calculated from this equation bandwidth from the equation A. We calculated the third formula for the quality factor. We already know that quality factor is equal to omega naught L over R, and it's also equal to 1 over omega naught RC. And from this equation bandwidth and quality factor, we got the third formula for the quality factor in terms of only the circuit elements. And in the last portion we defined that the resonant frequency is actually the geometric mean of the cutoff frequencies. So this was the summary of the last lecture. Now we are moving on towards today's lecture, and we will be discussing the energy analysis of the series RLC circuit. So we have two energy storing components in the RLC circuit, inductor and capacitor. So if we are going to start from the circuit, there is a resistor, inductor and capacitor that are connected in series, and the voltage across inductor is VL, across capacitor it's VC, and for resistor it is VR. And the input voltage, it will be Vm cos omega t. The current is IT. So this is the series RLC circuit. Now if we have to assume that the circuit is in resonance, then the impedance will be resistive. So at resonance the impedance is resistive because XL is equal to XC, and from there we calculated omega naught is equal to 1 over under root LC. Now if I have to find the voltage across the capacitor, so VC is actually the current through the capacitor into XC, where XC is the capacitive reactance, and if I will further write it down, so XC is J omega C, 1 over J omega C. And if I have to find the current at resonance, what is the current at resonance? That will be Vm angle 0 over R. So at resonance the impedance is resistive, so the current at resonance is Vm angle 0 over R. So if I'll put this current value in this equation, Vc will be Vm angle 0 over J omega Rc. Then if I will take this J in the numerator, the voltage across capacitor will become Vm angle minus 90 degree over omega Rc. So this is the voltage across capacitor in phasor form. Now if I have to convert this equation into time domain, so that will be Vct is equal to Vm cos omega t minus 90 degree over omega Rc. So if I will introduce the phase shift of 90 degree, the equation will become Vm over omega Rc sine omega t. But now what we have done, we were using the current value at the resonant frequency, right? So this omega should be omega naught, because with this current value, this is the value in which we have considered the impedance value equal to resistance, right? So if the impedance is resistive, so the omega should be omega naught, which is the resonant frequency. So in all the equations, omega should be omega naught. And what is the value of omega naught? We know that omega naught is equal to 1 over under root LC. So the final equation for the voltage across the capacitor will be Vct is equal to, this is omega naught, Vm over 1 over under root LC Rc sine omega naught t. So if I'll just simplify this one, so this will be Vct is equal to under root LC Vm over Rc sine omega naught t. So this is the voltage across the capacitor. Now to find the energy stored in the capacitor, so the formula for the energy of capacitor is half CV square, and this voltage is across the capacitor. And if I'll put this equation in the equation of energy of the capacitor, that will be half C LC Vm square sine square omega naught t over Rc square. So this will cancel out, and the final formula for the energy of the capacitor is half L over R Vm square sine square omega naught t. Now if I have to find the energy stored in the inductor, the formula is omega Lt is equal to half Li square, right? So this should be small I, and we know the formula of current that we already derived for the resonant condition. So half Li that will be Vmr cos omega naught t square, and the final formula for the energy stored in inductor will be Vm square L over 2R square cos square omega naught t. We have found out the energy stored in the capacitor. So this is A, and the energy stored in the inductor is B. So the total energy stored in the RLC circuit is and from A and B I can write it down as and from trigonometric identities I know that this is 1 and the total energy stored in the RLC circuit is the magnitude of the voltage square the inductance value divided by 2 into resistance square. So that is the total energy stored in your RLC circuit, which is a constant value. So at any instant in the RLC circuit, if you have to find the stored energy, it is a constant value. So if I have to show it by using a graph, for example, this is 0.5, this is the maximum energy and this is your 0. And the energy in one of the energy storing element is this, and the other energy storing element is like this. For example, if I assume that this is the energy stored in inductor and this is the energy stored in capacitor, and these are the changes with time, right? So at any instant the total energy will be a constant value. So if inductor is fully charged, the capacitor will be at 0 energy level. When the energy in the capacitor starts to increase, the energy in the inductor start to decrease. So at any instant the total energy of the RLC circuit is constant. So if I have to write it down, I will term it like that. There is a continuous exchange of energy between the magnetic field of the inductor and the electric field of the capacitor. So at any given instant, one is storing the energy, the other one is providing the energy. So it is a continuous exchange of energy between magnetic field and the electric field. And at any given moment, one element is storing the energy and the other one is providing the energy. But the total energy of the RLC circuit is always constant. So what we have done, we have calculated the stored energy in the RLC circuit. Now if we have to find the energy dissipation, so energy is always dissipated across the resistor, right? So if I have to find the energy dissipation, that will be the integral of the power that is dissipated across the resistor for the whole time period. So the dissipated energy is actually the integral of power that is being dissipated across the resistor for the whole time period. And if I will write down the power formula, that is actually I square R, right? So it will be 0 to T I square T R dt. We know the formula for I square that we derived in the start of the lecture. So it is 0 T and the value of current is Vm over R cos omega naught T square R dt. So it will be Vm square over R integral 0 to T cos omega naught T square dt. So after solving this integral, the final value will be Vm square over R into T by 2. So So that is the energy that will be dissipated across the resistor or across the whole RLC circuit. So now if I have to find the ratio of both the energies, ratio of energy stored and energy dissipated. So that will be omega S over omega D. So omega S was Vm square L over 2R square divided by Vm square T over 2R. So the final term for omega S over omega D will be L over RT. So where T is the time period, L is the inductance and R is the resistance. So this is the ratio of energy stored to the energy dissipated in the RLC circuit. Now we also know that omega naught is equal to 2 pi f, right? And this frequency is actually 1 by T. So omega naught is equal to 2 pi by T. And from here we can calculate the equation for time period. T is equal to 2 pi omega naught. So the above equation will become omega S over omega T is equal to L over R into 2 pi by omega naught. And after simplifying, that will be omega L over R into 1 over 2 pi. So the final equation will become omega S over omega D is equal to Q over 2 pi. The Q is the quality factor. Q is equal to 2 pi into omega S over omega T. So we have derived an equation in which the quality factor is actually related to the energy stored and the energy dissipated in the system. Actually this particular equation can be used for the other system as well, because for any system we can calculate the energy stored and energy dissipated, and we can relate it to the quality factor. So it can be used for the mechanical system or some other acoustic systems, because in all the system we usually have the energy, and energy is either being dissipated or being stored in any of the elements of that particular system. So we have derived a generic equation for the energy stored and dissipated, and we also defined it in terms of the quality factor of that particular system. So now moving on towards the second topic, which is the maximum voltage in the resonance circuit. So this is the second topic of today's lecture. Now we already know that at resonance the voltage across capacitor is actually the quality factor times the source voltage, and similarly for the inductor voltage it is again the quality factor times the source voltage. And we assume that this is a very large value, so the VC and VL are actually assumed to be large values. Because at resonance we have the maximum current, right? I maximum, because Z is minimum, impedance is actually equal to the resistance value, as XL is equal to XC. So the voltage is assumed to be a large quantity across capacitor and inductor, but they are actually out of phase. So now we are going to actually calculate what is the value for the maximum voltage and at which frequency does it occur. So is it occurring at the resonant frequency or is it occurring at some other frequency value? So we will start from the RLC circuit, that is we have some source voltage, a resistor, capacitor and inductor. So this is your Vs, CL, this is your Vc, right? So now what we have to find is the voltage across the capacitor or inductor, because we want to know whether it is the maximum voltage or value that is lesser than the maximum voltage value. So we will get the output voltage across the capacitor, Vc. So if I have to find the voltage across the capacitor, I will apply the voltage divider, and by applying the voltage divider, V0, which is actually equal to Vc, is equal to 1 by j omega c over r plus j omega L plus 1 over j omega c into Vs. So this is the source voltage, capacitive reactance, inductive reactance. We are finding the voltage across the capacitor. So it is the capacitive reactance in the numerator and the sum of all the reactances and resistance in the denominator, the actual impedance of the circuit as seen through the input. So V0 is equal to actually Vs over R j omega c plus 1 minus omega square Lc. So this is the voltage across the capacitor when the voltage divider is applied. So now if you have to find the voltage gain, so it is just bring this Vs in the denominator of V0. So this is the voltage gain and this is your transfer function. So if you have to write the transfer function, that will be V0 over Vs equal to 1 over R j omega c plus 1 minus omega square Lc. Now if I have to find the magnitude of the output voltage, so that will be V0. V0 is equal to Vs divided by under root 1 minus omega square Lc square plus omega Cr square. So in this term, what is the real value? In the denominator it is 1 minus omega square Lc, and the imaginary part is R omega c. So what I have done, I have just taken the magnitude of the source voltage in the numerator, and for the denominator the real part square plus the imaginary part square under root. Now what I want to find is the maximum voltage value, right? So now if I have to find the maximum voltage, I will apply the maximum value theorem. So that states that what I have to done, I have to take the derivative of the function, which is 1 over under root 1 minus omega square Lc square plus omega Cr square with respect to the variable. So in this particular equation, the variable is the frequency, and all the other quantities, the inductor, capacitance and resistor, they are the constant values. So what I will do, I will take the derivative of the output voltage with respect to frequency and make it equal to 0. So this is the maximum value theorem. So after solving that, I will get omega max is equal to under root 1 over Lc minus 1 over 2 R over L square. So this is your assignment number 1. So you have to take the derivative of this equation and prove that omega max is equal to 1 over Lc minus 1 over 2 R over L square. So this is your assignment number 1. So you just have to take the derivative and make it equal to 0, and whatever the frequency value you will get, bring it to the one side of the equality and take all the other quantities to the other side of the equality, and that will give you the value of omega max. And now if you have to find the value for the maximum frequency at which the maximum voltage is occurring in terms of quality factor and resonant frequency, we already know that omega naught is equal to 1 over under root Lc, and Q is equal to omega naught L over R. From here I can calculate the value of L over R is equal to Q over omega naught. If I will invert this equation, that will be R over L is equal to omega naught over Q, right? And for the second term, it is 1 over LC, so I will take the square of the equation, that will be omega naught square is equal to 1 over LC. So the second formula for the frequency at which maximum voltage occurs is actually omega naught into 1 minus 1 over 2q square under root. So we calculated two formulas for the frequency at which maximum voltage occurs. One is in terms of resistor, capacitor and inductor values, and the other one is in terms of resonant frequency and quality factor. Now from the equation, for example, omega max is equal to omega naught under root 1 minus 1 over 2q square. So this is the frequency at which maximum voltage occurs, right? So it is not actually occurring at the omega naught, which is the resonant frequency. So it is also dependent at the quality factor of the particular circuit. So if you have to make omega max approximately equal to resonant frequency, then you have to increase the quality factor. So if the circuit's quality factor is very high, then omega max will be equal to omega naught. Now if I have to find the voltage value, so what will be the voltage value, maximum voltage value? So I will start again from the equation that we calculated for the magnitude of the output voltage. So Vs over under root 1 minus omega square Lc square plus omega Cr square. So this is the same equation that I have written it here, right? So this is the same equation, magnitude of V naught. I'm using this equation to find the maximum voltage value, and in this particular equation, if I have to find the maximum voltage, so I have to use omega max value. So that is equal to omega naught under root 1 minus 1 over 2q square then I know that omega naught is equal to 1 over under root LC. So here it is LC, so I will take omega naught square is equal to 1 over LC, and from further solving it, LC is equal to 1 over omega naught. So I will use this value here. Omega max will be used for the values of omega, and for the values of RC, we know that Q is equal to 1 over omega naught RC, and if I will calculate the value of RC, it will be omega naught over Q. So we will replace these three equations in the first one, the first equation, and the final value of the maximum voltage across the capacitor will be QVS over 1 minus 1 over 4q square. Now from this equation again, the maximum voltage does not occur when the system is in resonance. It's also dependent on the quality factor of the circuit, right? So it is not occurring at the resonant frequency. So if you have to get the maximum voltage across the capacitor, then you have to increase the quality factor. So if the quality factor of the circuit is a very high value, then the voltage across the capacitor or inductor will be closer to the maximum value, right? Because if this Q is a high value, so this whole term will be a smaller value and the denominator will become 1. So V naught maximum across the capacitor will be equal to the quality factor times the source voltage. So this was the second topic. We have found the formulas for the maximum frequency and also for the voltage, maximum voltage across the capacitor, and we have proven that it does not occur at omega naught, or it is some other value of the frequency at which the maximum voltage occurs across the capacitor. But the maximum voltage and the frequency at which the maximum voltage occurs is dependent on the quality factor of the circuit. So if you have the quality factor which is a very large value, then the maximum voltage can occur closer to the resonant frequency. So this was the second topic of today's lecture. So now in this lecture we are going to solve some of the examples that are related to the series resonance circuits. The first example, it is just asking you to find the circuit elements that are inductor and capacitor. It is a series RLC circuit, and the properties of that circuit are, we are given with a resistor value which is 4 ohm. Then there is resonant frequency omega naught, the value is 4000 radian per second, and then the bandwidth of the circuit is given. Now what we have to find, we have to find the values of inductor and capacitance. We know that omega naught is equal to 4000 radian per second and bandwidth is equal to 100 radian per sec, right? Now if I have to find the value for the quality factor, that will be omega naught over bandwidth, and by putting the formulas I can calculate 4000 over 100 radian per second, and that will give you 40. So that is your quality factor. And there are two other formulas of the quality factor. Q is equal to omega naught L over R, is also equal to 1 over omega naught R C. So by using the first formula, we can write it 40 is equal to omega naught, which is 4000 radian per second, into inductance. What is the value of resistor? It is 4 ohm. So from here, inductance will be equal to 40 into 4 over 4000. So the value will be 0.04 Henry. So that is the value of your inductance. You can also use the second formula for the value of capacitance, and you can also use the formula of omega naught, that is 1 over under root LC. The capacitance formula will become 1 over omega naught square L. By putting the values of resonant frequency and inductance, I will get 4000 square into 0.04. The capacitance value is 1.56 into 10 raised to minus 6 farad. So for the capacitance value calculation, you can either use the formula of the quality factor, which is this, and you can also use the formula for the resonant frequency, which is omega naught 1 over under root LC. So the value, the answer from both the equations will be same, and the capacitance value is 1.56 into 10 raised to minus 6 farad. The second example that we are going to solve in this RLC circuit, we are given with a center frequency, and by center frequency we means it is a resonant frequency, and the bandwidth is given, that is 100 radian per second. We have to find resistance, inductance and capacitance. For the circuit elements, we will start from the formula of resonant frequency. Omega naught is equal to 1 over under root LC. So these are the values that we have to find. So we don't know the value of inductance as well as capacitance, so we cannot use this formula for calculating the values of the circuit element, but we can just write it as equation 1. Then there is another formula for quality factor, Q, which is omega naught L over R. We know the value of resonant frequency, but we don't know the circuit elements again. We don't know the value of inductance, we don't know the value of resistor. So this is equation number 2. We cannot use this equation as well. Now there is another equation, which is the relationship between quality factor and bandwidth. We know the value of resonant frequency, we know the value of bandwidth. So after putting the values of the resonant frequency, which is 1000, and the bandwidth value is 100, we got the value of quality factor is equal to 10. So if I will use the values known in the above two equation, omega naught value is 1000 is equal to 1 over under root LC. And then the second equation, it will become Q over omega naught is equal to L over R. So the final equation will be 10 over what is omega naught 1000 is equal to L over R, and it will become 0.01 is equal to L over R. So now we have two equations. The first one is from the resonant frequency formula, and the second one is from the quality factor formula. But in both the equations we have two unknown values. In the first equation we don't know the value of inductance and capacitance. In the second equation we don't know the value of inductance as well as resistors. So what we have to do is we have to assume one of the circuit elements. And if I will assume the capacitance value, I can get the value of inductance from here, and if I will have the value of inductance, I can easily calculate the value of resistance from here. So what I am going to do, I am going to assume capacitance value C is equal to 1 microfarad. Now solving equation number 1, we get 1000 is equal to 1 over under root L into 1 microfarad. So this will give you the value of 1 into 10 raised to 6 is equal to 1 over L 1 into 10 raised to minus 6. So this implies I will get the value of inductance is equal to 1 over 1 into 10 raised to 6 into 1 into 10 raised to minus 6. So that will become 1 Henry. So what I got, the inductance value is 1 Henry. Now I have found the values of inductance and capacitance. What I have done is I have assumed the value of capacitance 1 microfarad, and from there I use equation number 1 to calculate the value of inductance, which came out to be 1 Henry. Now using this inductance value in the second equation, this will become R is equal to L over 0.01 is equal to 1 over 0.01 is equal to 100 ohm. So by assuming the value for the capacitance, I have calculated the value of resistance as well as inductance such that the filter is acting as a band pass filter. We were already given the center frequency, which is omega naught, and the bandwidth values. So from there I have calculated the capacitance, inductance and resistance value. So this was the second example. We started from the energy analysis of the series RLC circuit, and we tried to find out the energy stored in the inductor as well as capacitor. So first we calculated the voltage across the capacitor, and from there we calculated the energy stored in the capacitor. Now to find the total energy stored in the RLC circuit, we added the energy stored in the capacitor, and in the inductor we got the value which is a constant, and it defines that at any given instant in the RLC circuit we have a constant energy stored in the whole circuit. So if the energy in the inductor is decreasing, the energy in the capacitor will be increasing at the same time, but the total energy will be constant. Then later we calculated the energy dissipation. After that we find the ratio of the stored energy and the dissipated energy, and we find the generic expression for the energy in terms of quality factor. And this particular equation, the quality factor and energy stored and the energy dissipated, we can apply this equation in any of the systems. It can be a mechanical one or the acoustic one. Later in the lecture we try to find the maximum voltage and the frequency at which the maximum voltage occurs. So we started from the series RLC circuit again and tried to find the voltage across the capacitor. From there we calculated the frequency at which the maximum voltage will occur, and we find out that higher the quality factor, higher will be the voltage across the capacitor at resonance, and if the quality factor increases, we will make omega naught approximately equal to omega maximum. So now in the next lecture we will be moving on towards the parallel resonance circuit, and that's all for today.